So first off, was the first substitution I did to write it as have u equal 2x?
Wait, can you repeat that? Sorry.
So you said I did a u and a v substitution. So did I do u equals 2x to begin with?
Uh-huh.
Okay, just wanted to make sure, because you could do it either way, with one being the u and the other being, or u being 2x and the v being the cosine, or vice versa. So just want to do it the way I did it. So first off, it's 1 over pi over 6 minus 0, since we're finding the average value, 1 over b minus a, times the integral from a to b of tangent 2x dx. And so the first thing we'll do is we'll turn that tangent of 2x into just a tangent of u by letting u equal 2x. And if u is 2x, then du is the derivative of 2x, which is 2 dx. And then in order to get rid of the dx, we need to have a 2 with it, turn it into the du. So we put a 2 inside, and we multiply by a 1/2 on the outside. Okay. So we'll simplify the constant out front first. Pi over 6 minus 0 is just pi over 6, and 1 over pi over 6 is 6 over pi. So we got 6 over pi times a half, which should give us 3 over pi. And then now we're going to integrate, and it's going to be the 2 dx will become a du, and then the tangent 2x will become a tangent u. So it's tangent u du. And then the lower limit was 0. So the lower limit now becomes 2 times 0, or 0. And the upper limit was pi over 6. So our upper limit becomes 2 times pi over 6, which is pi over 3. So you were good up to there, Rupa, yeah? Yeah. All right, so that's that. And then now, because we don't have an integral rule for tangent, which we could develop one, might be good to develop one just to know, so we don't always have to write out the u substitution. But we can rewrite this as 3 over pi times the integral from 0 to pi over 3 of sine u over cosine u du. And then we let v equal cosine u so that I can get rid of this thing in the denominator. And dv becomes the derivative of cosine, which is negative sine u du. And so I can get rid of the sine u du if I put a negative in front of it. So I'll put a negative in front of it and a negative in front of that. Those cancel each other out. And so now it's negative sine u du, or dv, over cosine u, which is just a v. So negative 3 over pi, integral of dv over v. And then now this becomes cosine of 0, which is 1, and cosine of pi over 3, which is a half. Does that make sense now or no?
Yeah, that makes more sense.
Okay. So, one thing, I don't know if I did this on the answer key, I probably did, because this is what I would normally do. I don't like having my lower limit being a larger value than my upper limit. And so we had rules for our integrals that said we could flip the limits of integration if we put a negative in front. And so if I put a negative in front of this, it'll cancel with that negative. So I can turn this into 3 over pi times the integral from a half to 1 of dv over v, which is probably what I did on the answer key. Flip the limits and flip the sign, which then gives us 3 over pi times natural log absolute value v, evaluated from 1/2 to 1. And now that I'm out of room, we'll give ourselves a new page for this. So it becomes 3 over pi times the natural log of, the upper limit was now 1, right? Natural log of 1. Is that right? Yeah, natural log of 1 minus natural log of a half. And that becomes 3 over pi. Natural log of 1 is 0, so that's just negative natural log of a half. And normally we don't like to have fractions in here. So we could bring this exponent of -1, or bring this coefficient of -1 in as an exponent of -1, which will make this 3 natural log of 1/2 to the -1, which is 2 over pi. Good or no?
Yeah, that made sense. I got mixed up when you like flipped the bounds and like the negative disappeared.
Okay. Yeah, that's one of our integral rules. Right? Remember, we had integral from a to a of anything 0. You can always flip the bounds and change it to a negative, add them, subtract them, those kinds of things. Those rules.
Are U substitutions pretty much just inverse chain rule?
Yeah.
Okay.
Not pretty much. That's what they are. They're undoing the chain rule.
Okay. Well, eventually, like the chain rule, will we have to be able to like do that in our head? Or are they more complicated with integrals?
So depends on what you want to do with your life, basically. Yes, you're going to need to, if you're going to do math and continue on and take a second semester of calculus, yeah, you're going to have to do simple U substitutions in your head for integrals. Otherwise, when you have to learn how to do integration by parts, your life is going to be god-awfully miserable. And you will eventually just learn to do them on your own because it just becomes so heinous not to.
Okay, cool.
You make it through this class without doing them in your head. But if you're going to continue on, you're going to have to do them in your head eventually. Yeah, simple ones like, like not that one necessarily. You could, if you're going to take another calculus class, you're going to just memorize what the integral of tangent is. So that one you would do in your head. Also, like, something like sine 4x, you should be able to do, you should be able to do that in your head. It's -1/4 cosine 4x plus your constant. If it's just like a little extra coefficient into it, you don't need to write it out, hopefully. E to the 3x, 1/3 to the 3x is the integral of that. You just kind of know the pattern and use it.
Okay, cool.
Other questions from homework or anything on that problem or just in general?
Kind of in general, but it kind of relates to this problem. When you took the integral of v or 1 over v and got the ln of v, why do you need the absolute value there?
Yeah, so that's what the formula says, right? But the reason why is if you think about the function 1 over x, right, that we're integrating 1 over x. This has a domain of -infinity to 0 union 0 to infinity, right? But if we take the integral of it, like we know the derivative of natural log x is 1 over x, right? So the integral of 1 over x got to be natural log x. But the domain of natural log of x, this just has a domain of 0 to infinity. But if we throw absolute value on it, that gives us a domain that is the same as the domain of 1 over x. So it encompasses all of the values that 1 over x does as well. And if you were to, let me see, I think I have Desmos open. So if you look at 1 over x next to natural log x, right? So 1 over, sorry, your slopes of natural log of x are 1 over x, and your slopes of -1 over x, or sorry, your slopes of negative natural log of x should be the same as the opposite of here. So if I put this inside absolute values, that'll hopefully help you see it. That these slopes are negative, these slopes are negative. The values are negative, the slopes are negative. The values are positive, the slopes are positive. And so they work out nicely like that. Does that help answer your question?
Yeah, thanks.
Mm-hmm. Other questions? Hopefully that homework wasn't too terrible. All right. We're going to talk briefly about accumulation problems. And these are problems in which you are given a rate at which something is increasing or decreasing, or a rate at which something happens, basically. So it might be a rate that we're consuming potatoes, or it might be a rate at which a water pump operates, or it might be a rate at which electricity flows through a current, or it might be, or flows through something, or it might be a rate at which waves crash onto the shore at the beach, or some sort of rate. And anytime we take a rate function and integrate it, we end up getting a numeric value of something. So think about it in terms of something simple here. This graph has nothing to do with this problem. But think about if we have a time and a velocity graph. Right? What do we get if we integrate velocity? What do you think we should get?
Time.
No.
Position.
You get a position.
Sure.
Right? So what's the derivative of position? The derivative of position is velocity. Right? And so the integral of velocity should be position function. So if we think about this in terms of what is velocity, well, velocity's units are whatever you want to do. Let's call them meters per second, right? And time would be in seconds then if this was a velocity and time graph that we had some function on here. Well, if we were to integrate it, and to integrate something, we find its area, right, underneath the curve, right? That's what an integral does. And so when we find those areas, each of the little sections of these that we get come from little rectangles that we draw, and we have an infinite number of rectangles. Remember doing that way back when? We drew a bunch of little rectangles underneath our curve, and we said we could get an infinite number of these little rectangles underneath our curve, right? And we would sum them all together, sum the areas of each of these rectangles together to find an exact value of the area underneath the curve. That's how we came up with this idea of the integral. Remember doing that?
Yeah. Yes.
Oh, good. All right. So what happens to the area of each of these? Well, the area is the height times the width. Well, what's the height? The height is a velocity, which is got a units of meters per second. And then the width has a time component to it, which is just seconds, and those cancel out, right? And so the integral, which is the area underneath this curve, goes from meters per second for the function here to a value in meters. It goes to an actual numeric value. Does that make sense? Or no?
Yes.
All right. So we're going to use that same idea here, except in this problem, it's going to be a way bigger eraser than I need, but that's fine. We're going to have, going up here, this is going to be our C of t function. Down here is still time. Okay? So time in this case is going to be in years, and C of t is going to be in millions of bushels per year. And so when I integrate the C of t function that is millions of bushels per year across a number of years from 1972 to 1973. We'll figure out the numbers for those years in a second. We should end up getting millions of bushels per year times years to find the area underneath of it, which just becomes millions of bushels of potatoes. Does that make sense?
Yes.
Cool. So these accumulation or rate integration problems are really popular on the AP test, and they will try to trick you with them sometimes by giving you some functions that are rate functions and some other functions that are not rate functions. We're not going to worry about that now. Everything we're going to do right now will just be with rate functions, and then as we get into our review with free response, we're going to take a look at how they're going to try and trick you and how you can deal with it. So all we need to do in order to figure out the number of bushels consumed from the beginning of 72 to the end of 73 is integrate 2.2 plus 1.1 to the t dt for the right limits of integration, and we should get the total number of bushels per year. So if t is the years since the beginning of 1970, so we'll say beginning of 1970 is t equals 0. What is the beginning of 1972?
2.
And what is the end of 1973?
4.
Should be 4, right? Because the end of 73 would be the same as the beginning of 74. And this is an integral that we could do by hand, but it's going to be a pain, and evaluating is going to be a pain, and we want to get an actual numeric value out of it that's reasonable for us. So we're going to use our calculators to evaluate this integral. Did I show you guys back in quarter, whatever it was, 1, how to use your calculator to integrate things, or no?
No.
No.
So unfortunately, at this moment, my graphing calculator that is embedded in my laptop is not functioning properly. So you're just going to have to listen to what I say. It should be easy enough anyway. You got your graphing calculator with you, I hope? Yes?
Yeah.
All right. You're going to hit the math button. And then you're just going to hit 9. It's option number 9 on your TI-83 or 84. And with any luck, for most of you, it will pop up an integral sign, and you'll put in your lower limit, you'll put in your upper limit, you'll put in your function, and you'll put in your d whatever. And for our purposes, whenever we plug these into our calculator, we're just going to type in whatever variable we happen to have as an x. So in your calculator, you'll put your lower limit is 2, your upper limit is 4. You'll type in 2.2 plus 1.1 to the x, and then you'll put dx. Now, does anybody's calculator not pop up an integral when you go to math in option 9? Does anybody say FNINT?
Mine does.
Okay. So if yours says FNINT, here's what you need to do. You need to type in your function after the parenthesis there. So you'll do 2.2 plus 1.1 to the t, comma, which the comma, I believe, is down somewhere near the bottom of your calculator. Type in x, another comma, lower limit, another comma, upper limit, and then end your parenthesis.
Okay, thank you.
And what do you guys get when you do that?
7.066.
7.066 millions of bushels of potatoes. Perfect. And make sure you always attach your units to it. And make sure that on the AP test, you always round to 3 or more decimals, never less than 3. Did everybody successfully get 7.066 millions of bushels of potatoes?
Yes.
Wonderful. All right, let's do another one. This one we got a chart of values. Fun. So I'll give you a second to read through the problem, and then we'll start talking about it. All right. So we got a pump that is connected to a generator, and it's pumping, I don't know, pumping water, does it say here? I don't know. Pumping something in gallons per minute. And so we've recorded exactly the rate at 5-minute intervals for an hour. And we want to know how many gallons were pumped in that hour. So we're looking at a rate function, gallons per minute. And we want to know the number of gallons. So we will integrate it across time. Okay? So we need to integrate from where to where.
Would it be 0 to 60?
0 to 60, our function, which we don't have a function, r of t, dt. And so we have to come up with, since there's no actual function, no explicit function for this, we have to use some method to approximate this integral. Anybody have a preference on that? Okay, I do. The trapezoidal rule. So, trapezoidal rule says what? H over 2, right, which is b minus a over n. So b is 60, a is 0, 60 minus 0 over n. How many subintervals do I have here between 0 and 60 if I have 5-minute intervals?
$12.
12. So that's b minus a over n divided by 2 for the trapezoidal rule. And it'll be the first value, and 2 times the second, 2 times the third, and so on until we get to 2 times the second to last, and then 1 of the last. And so it's a fair amount of unpleasant little arithmetic there, but not too terrible, I'm sure. What do you get?
I got 3,882.5.
Uh-oh.
Don't think I did that right.
I don't think so either. Actually, you could have. That could be fine. What did you get? Sorry, 3,000 what?
3,882.5
gallons. Let's see. Let me think about that. 12. Yeah, that seems reasonable.
I got 3,582.5.
I got the same thing as Alex.
Let's see here. Yeah, I think it's going to be a little less than 3,800. Yeah, 3582.5. That seems to be the consensus. A couple people have sent me direct messages with that. I think you might have just added one too many 60s in there at some point. We can say that it's going to be around 3,600, right? Because, and both answers seemed reasonable enough, but we have 12 of these intervals, right, which is 60 total minutes, and it's gallons per minute. So 60 minutes at about 60 gallons per minute should be about 3,600 gallons. This seems reasonable. And it looks like we got 6 of them that are below 60, and then 4 that are above 60, and 2 that are at 60. So it should be probably a little below. Yeah, sounds good to me. Any questions on that?
Nope.
All right. Let's take a look at another one. I'll give you guys a second here to read it, and then we'll start talking about it. All right, so we've got an amusement park. We got people entering the amusement park. We got people leaving the amusement park. We have some people in the amusement park to begin with. We want to know how many people are still in the park at 6 p.m. And so to break this down into even more basic terms than math terms, how would we figure out how many people are in the park at 6 if we know the number that are in the park at noon? It would have to be the number at noon plus the amount that enter from noon to 6 minus the amount that leave from noon to 6. Wouldn't that do it?
Yeah.
Okay. So this should then be 3,000, which is the number at noon. And how many will enter between noon and 6? Well, we're given a function here, E of t, that represents the rate at which they enter. So the number that enters should be the integral of that from 0 to 6. And what should be the number of people that leave from noon to 6? Well, we're given a function L of t that is the rate at which people leave. So that should be the integral from 0 to 6 of L of t dt. Good or no?
Yeah, good.
Okay, so then how are we going to find the values of those two integrals?
Well, they give us the equation for L of t, so we can just plug that in. To
Right, that one should be
calculator.
easy, right? The integral from 0 to 6 of L of t will just integrate that corresponding equation. All right, so somebody tell me what that is. This we'll just use our calculator for.
I got 2,106.4 roughly. I don't know.
2,106 point. All right. Somebody else confirm that. Sound about right?
I got that too.
Good. All right. And then what about the E of t integral from 0 to 6? How are we going to find that?
Could we use what we just learned the other day about like average height to find like the area under the curve of something, or is that not related?
I mean, I think you're half on the right track. We don't need to use what we learned the other day about the average. I mean, we have a function there, right? Looks like that's linear, and that's linear. We should be able to find the exact area underneath that curve, shouldn't we?
Yeah.
Yeah, so there's a trapezoid, a rectangle, and another trapezoid, right? Rectangle in the middle should be easy. What's the rectangle in the middle? 1 times 600. So 600. And the trapezoid, this one, ought to be base 1 plus base 2, right? 400 plus 600 divided by 2 times the height, which is 3. And what does that come out to be? 1,500. And this one ought to be 600 plus 500 divided by 2 times the height, which is 2. So this ought to be 1,100. And so we should have an exact value already of the number of people that enter. What should it be? Should be
3,200.
3,200. And so 3,000 plus 3,200 minus 2106.4 gives us what?
$4,093.6.
4,093.6 people. Well, we'll round that. I don't think we're going to have part of a person. If the person isn't halfway through the exit already, we won't count them as having left. So we'll call it 4,094 people. Good or no?
Good.
Cool. All right. So as we mentioned a minute or two ago, also, we can sort of apply this idea. We did this at the very beginning, right, with velocity. Well, we should be able to use that to, for given a velocity function, find some information about the displacement of the object. So if we integrate a velocity function, we're getting a position function. And so if we look at how far something changes from its initial position, we should be able to figure out where it is at its later position. And this is sort of, or at its later time. And so this idea is the beginning of what we start to call differential equations. And we're going to sort of get into talking about differential equations now. So, in fact, maybe we should come back to the velocity stuff in a couple of minutes and just talk about what a basic differential equation is first. Let's do that. So I already have those notes open. Yeah, we should talk about that first. So any equation that we have that involves a derivative within it is called a differential equation. Okay? And we can talk about different orders of differential equations, meaning we might have a higher derivative than a first derivative. So this differential equation that's written here is dy dx equals secant squared x plus 2x plus 5. That is a first order differential equation because it has a first derivative and only a first derivative in it. There are no higher derivatives than a first derivative. If it was the second derivative is secant squared x plus 2x plus 5, then it'd be a second order differential equation. And so when you are given a differential equation, what you are being asked to do is to find all of the functions that satisfy that differential equation. So, you know, when you're given a linear equation or just like an equation in one variable, x plus 7 equals 2, or, you know, or x squared equals 4, and you're asked to solve the equation, what are you doing? You're finding all x values that satisfy that equation. Well, the same thing here, except now we're finding all functions that satisfy this differential equation, that satisfy this derivative. And so how would we find a function that satisfies this derivative? What do we need to do?
You differentiate the right side.
We need to what? I missed the first word that you said.
I said differentiate.
No, we don't want to differentiate the right-hand side, because if we take the derivative of it, that's not telling us a function that has this as its derivative. We need to anti-differentiate it, we need to integrate it in order to figure out a function that has this as its derivative. So in order to do that, we'll take this dx, bring it over here, and we will integrate both sides of it. And what's the integral of dy? That's just 1. The integral of 1, which is, if we're doing it in terms of y, should just be y. And on the other side, the integral of secant squared x is
Tangent.
tangent x, and the integral of 2x is x squared, and the integral of 5 is 5x. And what have we not done here?
Plus constant.
Plus constant. What about over here? Shouldn't there be a constant over here? Yeah.
So do the constants cancel out, or no?
Yeah, so we don't need to actually put a constant on both sides, because a constant over here and a constant over, they don't cancel out, but a constant over here and a constant over here could be combined onto one side to just be a singular constant. And so rather than writing a constant on both sides, we'll just put the constant on the side with the x and say this is the general solution to that differential equation. This represents all possible functions that when you take their derivative, give you secant squared x plus 2x plus 5, right? Derivative of the tangent gives you the secant squared, the derivative of the x squared gives you a 2x, the derivative of the 5x gives you a 5, and the derivative of any constant plus 1 minus 7 plus 8,000 pi they all just become 0 when you take their derivative. Right? Nothing really different here other than we just integrate. True so far.
So how is this different than any other like integral? Then what makes it special?
Well, it's not really different, except that what we're doing is we're solving for the function that has this thing as its derivative, rather than integrating something to look for the area underneath the curve. And what's going to be different is when we move to the next page and I say, all right, we're no longer looking for the general solution. We are looking for a specific solution to this differential equation that satisfies some initial condition. So I'm going to tell you, okay, I need x to equal 1 and y to equal 3. So that when I plug in 1 for x and 3 for y, it has to be true. Which means what we're going to be doing is we're going to be finding specific constants that that solve the differential equation, or that need to be added to the integral to give us a solution to the differential equation, to give us a specific, or we call them a particular solution. So that's what we're going to do now. We're going to get an initial condition. And sometimes we call these initial value problems. They're still fairly basic differential equations, but the idea is we want to know the singular solution to this differential equation, so the antiderivative of this, that when you plug in 1 for x gives you 0 for y. So we're looking for a specific value for the constant. Does that make sense to everybody?
So we're just going to integrate and then plug in the values, or?
That's it. It's easy. It's not difficult.
Okay.
It shouldn't be difficult. At least not yet. It will eventually get more difficult. But as of right now, it shouldn't be very hard. That's exactly what we're going to do. We're going to bring the dx over. We're going to say dy equals e to the x minus 6x squared dx. We're going to integrate, and we're going to get y equals, what's the integral of e to the x?
E to the x.
E to the x, and what's the integral of minus 6x squared?
3x, or 2x cubed.
Plus some constant. And we know that I want x to be 1 and y to be 0. So we're going to plug that in down here. Y will be 0 and x will be 1. And we need to find the actual constant. So this is just 0 equals e minus 2 plus c. So what does c equal?
2 plus e.
2 minus c, right? Yeah, subtract.
Yes.
And so our final answer here should be y equals e to the x minus 2x cubed plus 2 minus e. Good or no?
I thought you were just solving for c. I thought that was like the final thing you wanted to do, but then you plug it back in. Is that the thing? And then
Yeah. So we are looking, so the question says find the particular solution to this differential equation. So the particular solution, remember from the first page, is we find all functions that satisfy it. Well, there's only one function that satisfies this condition, that the derivative is this, and that it goes through this point. Does that make sense or no?
yeah, I think it does. Yeah.
Cool. And if we take the derivative, what's the derivative of e to the x? It's e to the x, and the derivative of 2x cubed minus 6x squared there. Derivative of 2, 0. Derivative of negative e, also 0. Those cancel out. So we do have this derivative, and if I plug in 1, we get e minus 2 plus 2 minus e equals 0, which it should.
So will this be like the rough setup for like all differential equations problems, or is this just like the very beginning to like a
It will.
much harder?
It's going to get more difficult, but it's there's
It's like
really
the same concept.
For
I'd
our
like just
purposes, there are two levels of differential equations to solve. This is level 1. This is easy. Level 2 is more difficult and has a generally the same setup, but there's other stuff that we got to deal with too, which we will get to tomorrow. But for today, they're mostly going to be this easy. There's one other thing we need to add to this in a couple of minutes here, but that are still the level 1 easy ones. But this should be pretty straightforward, is my hope. So we're going to do the same thing here. So we're going to bring the dx over and we're going to integrate. And we want to have a y-intercept of 3 for our final solution, which means that when x is 0, y is 3. And so we integrate the dy to give us y. The dx is over here. So we integrate the sine x to give us what's the integral of sine?
Negative cosine of
Negative
x.
cosine x.
Cosine. And the integral of the 2x is plus x squared.
X squared.
Plus some constant. We'll plug in 0 for x and 3 for y. Cosine of 0 is 1. So this is -1 plus c is 3, or c is 4. So easy enough. Our final solution here should be y equals negative cosine x plus x squared plus 4. Good or no?
Good.
Great. All right. We still got some time. Let's do another one. What should we do first? Bring that dx over, right? And then integrate both sides. Y equals x squared over 2 minus, what's the integral of secant squared?
Tangent.
Tangent x plus some constant, right? And when y is 3, x needs to be 0, which tells us that the constant is
3.
wonderful. And so our final answer is y equals x squared over 2 minus tangent x plus 3. Everybody good there or no?
Yeah.
Okay. Now, there's an issue with this one. This is correct in a sense, but there is something else we have to deal with here. How is this function different than the last two with the initial conditions that we had? So x squared over 2 minus tangent x plus 3. How is that different than negative cosine x plus x squared plus 4? And different than e to the x minus 2x cubed plus 2 minus e? There's something different about this one.
It's 2 lines instead of 1 point.
What do you mean?
Like y equals 3 like creates a line all the way across, and so an x equals 0, so they like intersect at a point, but they're continuous.
I'm not sure what you mean. They intersect at a point, but they're continuous. You're saying this y equals 3 right here as like a line?
Yeah, I
Yeah,
don't know if
so-
that has anything to do with it.
No, it's just that this is, I'm just saying this is the 0.03, that this has to go through the 0.03.
Okay, got it.
Yeah, not that that's a specific line. All right, let's real quickly, let's go back to Desmos here.
Is it
What
because
was- What?
tangent of 0 has multiple solutions?
Tangent of 0 doesn't have multiple solutions. Tangent of 0 is 0, but it does have to do with this tangent. What
What's
can you
up with
tell
the
me about
tangent?
tangent?
Sine of a cosine.
Asymptotes?
It's got some asymptotes, right?
Uh,
Anything in here have asymptotes or any sort of discontinuities at all?
no,
What about here?
no.
No. But here, vertical asymptote. Okay? Because there is this discontinuity, we have to do something called looking for the interval of validity. Okay? And so a differential equations solution is technically only valid on the continuous part of the function that includes the initial condition. So we're going to say that our solution is only valid on the continuous piece, and we're going to say on one continuous piece of the function that includes the initial condition. In other words, we are pinning down our function with this constant of 3 on the interval that includes x equals 0. But on all the other intervals, we got any constant we want. It doesn't matter, because the only section that we care about the constant having to be 3 is the one that includes x equals 0. And so where are the asymptotes for this? This should have a vertical asymptote at x equals what?
Pi halves.
Pi over 2, and 3 pi over 2, and 5 pi over 2, and 7 pi over 2. Also negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, and so on, right? It's got an
Yep.
infinite number of these asymptotes. Every pi units on increments of pi over 2, it's broken up, right, by a vertical asymptote. We could look at the graph of it if we wanted to. What is it, x squared over 2 minus tangent x plus 3? Right, if we zoom that out a little bit, we can see there's an asymptote every pi over 2 units, right? We could type it in here, x equals pi over 2, right there, right? X equals 3 pi over 2, got another one right between those, right? 7 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, negative pi over 2, and so we got these asymptotes everywhere. Everybody see that and agree with that?
Yeah.
So between which two asymptotes does our initial condition of x equals 0 sit?
Pi over 2.
That's only one. Between which two?
From negative pi over 2 to pi over 2.
There's one at negative pi over 2, there's one at pi over 2, there's nothing in between there. And that is the interval that includes x equals 0. And so this is the only interval on which this solution is guaranteed to be valid, to be the only thing that works. We could have any other constant on any other interval and it doesn't matter, right? But on this interval, negative pi over 2 to pi over 2, that includes that initial condition, we must have a constant of 3. Does that make sense to everyone?
Yes.
Wait, but Isn't negative pi over 2 less than 0? So why is that? I'm not quite making the connection of why.
This
That's
is the
included.
continuous portion that includes x equals 0. Right, so if I zoom in here, right, between, we'll turn this one into negative pi over 2. Between those two lines is where x equals 0 falls, between this asymptote of negative pi over 2 and this asymptote of pi over 2. That's where our initial condition is, that x equals 0, y equals 3. And so
Oh, I see. Okay.
that's why we choose that interval. And we don't care about any of the other intervals. Pi over 2 to 3 pi over 2 couldn't possibly care less what happens in there. It couldn't possibly care less what happens between 3 pi over 2 and 5 pi over 2, or negative 11 pi over 2 and negative 13 pi over 2. I don't care. All I care is that this one in between here has to have a constant of 3. Otherwise, I don't get that y-intercept of 0, 3 that I was looking for.
Okay.
So, and you don't necessarily need to look at the graph to find that interval, because hopefully you should be able to go in here and say, well, I know these are where the asymptotes are. And so there's a continuous portion between like negative pi over 2 to pi over 2, one from pi over 2 to 3 pi over 2, one from 3 pi over 2 to 5 pi over 2. There's all these little continuous sections. We just look for the one of those continuous sections that includes x equals 0. And I know you sent me a question, Lindsay, about that. Does that answer your question, Lindsay? If it's helpful to look at the graph, you can, but it shouldn't be necessary. Yeah. Okay. Everybody good there?
Yeah,
so
so
for
once you
these-
make that condition, you're all good. Like it's correct
Right.
now.
Yep. Yeah, and so for these other ones, we don't need to specify if the domain is just negative infinity to infinity. If it's continuous for all real numbers, we don't normally specify. We could have said for negative infinity to infinity if we want to, but we don't normally specify if the interval of validity is all real numbers, then we don't normally have to put it. But if there is a discontinuity in it, you must break it down. So, good or no?
Good.
All right. Let's do one more of these before we're almost out of time, huh? Let's do one more. So, dA dt equals 1 over t minus 1 over t squared plus 6. And we've got the initial condition that a equals 0 and t is 1. So we'll bring the dt over and we'll integrate. The left side, the integral of dA is just a. And over here, the integral of 1 over t is a natural log absolute value t. And the integral of minus 1 over t squared, that's negative t to the negative 2, right? So what should that become? What's the integral of negative t to the negative 2? Go up to negative 1, divide by negative 1.
1 over t.
Positive 1 over t, and then plus 6t plus a constant. And when a is 0, t is 1. And so what's our constant? Constant should be
Negative 7.
7. So we end up with a equals natural log absolute value t plus 1 over t plus 6t minus 7. And where does this have discontinuity? T cannot be
0.
0, which means that the domain would be negative infinity to 0, 0 to infinity, but we only choose the single section that includes t equals 1. So this will be for what interval?
0 to infinity.
0 to infinity, because that's the one between those two options, that includes t equals 1. Everybody good there? We're going to do a lot more with these next time. That's the basic intro to differential equations.